Okay. Yeah, sorry for the slight delay. There's always some technical issues. And welcome to the people who are joining us online. So it's a great pleasure to welcome Philipp U Haselbach from Danish Technical University, DTU Wind in Copenhagen. So over to you.
Thanks, Johan. Yeah, it's an honor for me to be invited here and to give you a presentation. So I wasn't 100% sure what I should present. So then I thought I will give you a broad overview about the activities that we do. It's about blade design and enhancing the reliability of wind turbine blades and also the manufacturing aspects of that one. But before I want to look more into dig deeper into the topic, I just want to give you a short presentation of who I am. So as I said, my name is Philipp Haselbach. I'm working at the Technical University of Denmark, DTU Wind and Energy Systems. And I studied in Germany production engineering with specialization mechanical engineering. And then I came to Denmark and did my PhD there on the topic ultimate strengths of wind turbine blades under multi-axial loading. So basically, I was looking into wind turbine blades under loading not only flatwise or edgewise, but a combination of those. And then looked into some damage mechanics and tried to model with cohesive elements how the damage grows in particular areas. Afterwards, I just stayed there, did my postdoc, worked as a researcher, and then became associate professor. Yeah, as I said, I'm working for the Institute of DTU Wind and Energy Systems, and we just got a new vision. So DTU was always there that we should make science for society, so that should be more applied and should be for the benefit of all people. And our vision is to have a society fully powered by renewables with wind as a backbone, because of course we are the wind energy department. And our mission is that we should lead by scientific excellence. And usually we have 4 pillars that our foundation is built on. One of those is research. So our research should be world-class, leading, but also applied. So most of our research is really applied, and we have a lot of collaboration with industry. We have also a little bit basic research, but I would say most of the research is applied. Also a little bit due to our historical background. Wind energy was before the National Research Institute for Sustainable Energy that was then incorporated into the Technical University in 2010, I think. And those before it was really like a research laboratory more. Then of course innovation is one of the other key drivers. There we have a lot of areas where we try to improve and come up with innovative things. So that's on one side remote sensing. Then we do a lot of work on hybrid composite materials. But I think we are also known for some of our software suite that we have in software applications, where we always try to develop further what we offer. Of course, a big thing at the moment is digitalization and trying to predict everything in real time. And where we work on different tools to allow that to be more in the data-driven environment and try to provide users later on also tools where they can in real time analyze their equipment or machines and having impact on the managing tools. But of course, another important aspect is also our education, because I'm also getting older and we need a new generation. And the new generation, of course, should be even better than what we do. It's, of course, difficult because it's facing more and more challenges, I would say. Everything becomes broader, and you also have to adapt to large language models. So incorporating ChatGPT and other large language tools into our education program is also one of our key aspects there. But in general, we offer courses for master students, PhDs, and bachelor students. But we also have quite a huge amount of massive open online courses, Coursera courses, and also a lifelong learning program that we offer for persons that are already in work but would like to change maybe from oil and gas industry towards wind energy and would like to know a little bit in particular areas a little bit more. There we offer courses. And then beside education, research, and innovation, we also have scientific advice. So that's our commercial aspect, you can say, where we do consultancy for companies or and I think that's also, of course, important because on one hand, it's a good income source for DTU when we do experimental testing, characterization of materials, and so on. But also, it's always a kind of for us to be state of the art because industry is in some areas leading; they are ahead of us. And when we collaborate with them, then of course we also get the knowledge back from industry. So it's quite beneficial, I would say, for both sides. Sometimes they outsource their R&D activities. They don't have maybe the manpower, and then they work together with us. Yeah. One key thing that we have at DTU is developed software, and I think some of the software is well known. Original Riese campus where we located was a nuclear power plant, the only one in Denmark, founded by Niels Bohr. And then they were, of course, afraid if something happens with a nuclear disaster, how will all this radiation be transported in which direction? So traditionally, they had a quite good methodology department there, doing all the wind forecasting. And based on this knowledge, DTU built up a wind resource assessment and siting tool. And I think that is used all over the world to see where are really good locations to site wind farms and what type of wind turbine should be erected and so on. But then we have a lot of other tools, aeroelasticity programs like Hawk2, but also smaller tools for niches, I would say, like BCAS, the beam cross-section analysis software that is part of the section I'm working in, where we develop a cross-section analysis tool where we can go really into detail in kind of 2D and analyze the stresses and strains and couple that then also with other tools where we have quite rudimentary beam elements when we do multi-body analysis and couple that into this beam code where we get high resolution of stresses and strains. Yeah, in total, besides from the software, we also have a research infrastructure, a lot of laboratories, different laboratories. We have a national wind tunnel, the Polar Tour tunnel. Then we have a material lab that is also part of the division I'm in, where we do everything from small scale testing up to 1.5 meter components. And this is then complemented by our large scale facility where everything that is above 1.5 meter, you can say, we test in there up to wind turbine blades of 45 meter lengths. And 45 meter lengths, you might say, this is not big any longer. That's true. We also are part of a commercial research or commercial test lab where we can test the state-of-the-art wind turbine blades more than 130 meter long. But our large-scale facility is a pure research facility where we had the aim that we want to test a little bit smaller downscale wind turbine blades or older wind turbine blades because a lot of the phenomena that we can see in wind turbines, we can also showcase on smaller wind turbine blades, and there it's not so costly to handle them. Yeah. Good. Then just to the manpower here, employees. We have around about 450 employees now. 26% are women. We would like to increase this amount. I think our female PhD students are around about 30%. we always like or would like to attract even higher amount there. And I think also in the last year, more and more female professors were appointed there, also to showcase the importance there. Yeah, but in general, we are quite diverse. We have, I think, more than 60 different nationalities. In the beginning, it was always the idea that we should have 50% roundabout Danish and 50% foreigners, so that the foreigners also come with new research idea to the institute. I think nowadays we are even more than 50% foreigners in there. Yeah, and then one of the last slides to our organization is how we are built up. We have one head of department, it's Morten Jeppesen, and then we have basically 4 research divisions, and each division has around about 110 people employed, where we have our wind energy materials and components division, where I'm part of, where we do everything from really small scale testing to the structural big components, but it's still on component level. Then we have our wind turbine design section, and there it's more holistic, looking into the wind turbine, but more isolated the wind turbine, but also the interaction between the wind turbine blade and the towers, and looking into frequencies and so on. And then we have wind energy systems. They look into the bigger perspective, where they place several wind turbines into wind farms and look into the interplay there. And then, of course, we also have power energy systems, which is then connecting the wind farms to the grid and having power tweaks and other aspects there, and also looking into the methodologies. So, yeah, and then we have one unit that is also shown here, being on the same level, but it's basically our support functions, the administration and business support. Yeah. Good. So where are we located? We are located in Denmark, and you can see Copenhagen. It's round about there. So it's on the island Zealand, and that's quite close where we are located in Lyngby campus. Can I move this one? So Lyngby campus, that's close to Copenhagen. I think it's basically more located here. It's 13 kilometers from Copenhagen. That's where DTU has a main campus, but we as DTU Wind Energy, traditionally we were placed close to the fjord at a Riese campus, where I would say more than 350 persons from our institute are placed, and where we also had small research facilities, all our labs. But then we have 2 extra sites, that's Østerild and Husør, that's in Jutland, and that's a big test site for really big wind turbines, where we have almost offshore wind conditions, and those make it really attractive for industry to test the newest wind turbines, as for example the new Siemens, I think 21 megawatt wind turbine that is right now erected there. So it's basically a site that we own, and we rent out the test sites. Good. Okay, but just coming to the Riese campus where we are placed, I want to go now into a little bit more details about the blade design and enhancing reliability and manufacturing. So you can see here the loop. So basically we are now able to have the entire loop of a wind turbine blade production in-house. That of course starts with the material characterization, where we do basic tests to get the material characteristics out, like stiffness and so on. And then we go to the design process, when we can manufacture our own wind turbine blades, we can produce it on full scale, do design of experiments, and then also conduct experimental testing in our large-scale facility, and in the end, of course, validating all our models. And I just want to show you how in the entire loop, digitalization and coupling our physical products with digital products merges and where we see benefits. Yeah, let me just start. When we have the wind turbine design process, it's an iterative design process where we start usually with the aerodynamic airfoil design. So for different cross sections, coming up with the best airfoils and then lofting them together, then trying to fit structurally it together so that we have a load carrying structural blade design as well, and not just only a good aerodynamics. And then, of course, we feed it back to our air elasticity tool, where we look into the dynamic aspects of the incoming air together with the structural stiffness that we provide, and see how the blade deforms if we have enough tower clearance when the blade is rotating and not hitting the tower, or if there are interferences, and so that we don't get into oscillation or high frequencies where maybe the blade would start in resonance to the tower and everything would collapse. And of course, also extracting the loads that then again are applied on our structural components. For the structural design, we have developed over the years a blade modeling tool, and this blade modeling tool is, we have different versions of it, but the newest one is Python-based, I would say, where we have one source code, and this source code then creates in a block by way. So for different block or modules of blocks for the wind turbine blade, describes very detailed the entire layout and design of it. In those we can put it into commercial fine element software like Abacus, for example, where we also have a built-in user subroutine. But we can also use our beam cross-sectional analysis tool, BCAS, or we can use it for creating the stiffness metrics for air elasticity codes, so multi-body simulations. We can derive full 3D brick elements or thin shell elements. So this tool allows quite a lot of things. And the idea behind it is always having the same origin for the software, so that each blade model that is built up should be detailed enough described so that not due to different modeling approaches, we have variance when we compare different software. Yeah, I said, for example, when we look into 2D, then we can go really into detail and look into the different stress states. So when we design a blade, then usually we are quite confident in what we do. But of course, in some details, like for example, the wood inserts, we also complement it with structural testing. So first we design it on the computer, come up with maybe a novel idea where we want to have different layups. And as you know, maybe there are different approaches. One of the approaches is the IKEA solution, where you just drill in from the outside of the wind turbine blades a kind of hole for a barrel nut, and then you have this IKEA or T-joint approach where you put a barrel nut in and then you have joints. Here we rotated by 90 degrees because we thought it might be better. And then we tested everything. And there, I think it's the first time where we then also couple our numerical simulations with digital image correlation systems, where we can see then how the stress fields that we predicted matches with what we see. And of course, also ordinary strain gauges and so on the structure. And in this particular case, we try to predict. What you can see is the inner part that is over-laminated or attached to another part. Then we want to predict how much it can resist before a separation occurs there. And of course, model that also with damage mechanics. And yeah, we got a quite good representation of our numerical simulations. And of course, there you can say what is new in here. I think a lot of people have done so, but with each step where we do it and try to couple it, we get, of course, closer and more towards our vision to do virtual structural testing. So when we have confidence in the method once, then we know we can adapt it and we don't have to test it again. Yeah. So then, of course, when we have confidence in the small aspects, we also look into the bigger aspects, look into the entire wind turbine blade, and then, as said before, trying to ensure, for example, that we can carry the loads, that we don't run into any buckling problems that we have now, tower clearance and so on. And then usually we release it for production. As said, when we do scientific advice, we also do consultancy for companies. But also in this case, we build up our own wind turbine blade, where we also manufacture the mold. And here, one of the aspects is then that, of course, we had a CAD model as designed our wind turbine blade, and now we build a mold. And everyone knows when building a mold, you have small deviations. So we scan the mold with a 3D scanner. Then we got a high resolution of our mold, and then we feedback this grid or the outer surface of our wind turbine blade mold back to our fine element program, and those can update or create a new fine element model that includes small imperfections or deviation from our CAD model. And those we have a kind of digital twin because our outer shape now is adapted to it. And we also did then, after we manufactured the first inner part of the, or the first two shells of the blade, we also scanned the inside so that we knew exactly the height of the wind turbine and tried to map it, but we haven't, not that we have not succeeded, but we haven't accomplished it fully yet. But that's the idea, that we also know, okay, is the height, the stack height that we modeled, is it living up to what we really manufacture? And yeah, so basically when it comes to manufacturing, we have the traditional way, our real manufacturing way, where we start with a layer, then we do the infusion, the curing, the finishing, where we demold it and do then the testing. But of course, we want to enhance this by the virtual manufacturing. That means so far, the wind industry has relied a lot on trial and error. And I think we will see a nice Viva from Oliver later on today, where Oliver also looks into the infusion, stimulation and curing models and prediction of those. And we do the same at DTU because we believe there's a lot of potential to save. I think, Oliver, you managed to reduce the cycle time in some areas by 40%. That's quite a big achievement, I think. It's really impressive, but it shows what kind of potential is there when looking into simulations of that and really making a disruptive approach, and not only stepwise over 1 or 2 years by a lot of iterations, but looking into numerics and really trying to improve it. And that's the same what we do. So of course, all that requires also high input characteristics, so high quality and reliable material characteristic in the beginning. So where you have to do fabric characterization, so for the permeability, so that you know how easy the resin can flow through the fabrics. You want to have know really the impact of the consumables on the flow. So when you do infusion, and now I don't know all the background of you, but usually you put your dry plies into a mold, and then you have some flow mesh on top that allows or enhance the resin to be transported during the infusion process. And these are consumables, and they can also have an impact on the flow itself because they have a specific grid, and depending on how the grid is laid up, the resin is flowing a different way. And all that we analyze as well, and also looking how the flow goes through core materials. And that's of course important because, as stated there, if you have garbage in, you get garbage out of your simulation. Even so you get a colorful picture, it's always important that you really focus on having good quality in there. For that reason, we build up experimental labs where we can do the characterization of permeability of the materials. So it's based on the Darcy, but where we do it in 3D as well. I think that should be quite familiar to you. So the resin is coming from the top and then spreading around, and then we do is photo imaging. We look into how the resin is spreading in the material, and then usually it's a kind of ellipse form, and then we track the flow front, and with that we can derive some material permeability values that we later on need for doing good simulations. Another way, of course, is also doing a virtual prediction of fabrics, where you can do an X-ray scan of your material, and from that try to predict the permeability. And we have done so. We have also done with virtual prediction of it, where we just model the fabrics. And then we have three tools. Basically, we have our experimental characterization, the virtual prediction due to X-ray scan, and then the modeling aspect. And we could see when we compared all three methods on the most current materials that we use, it matches quite well. And that's, of course, important, and we have more confidence in the material input parameters that we need for our simulation. Yeah, then I said, impact of consumables on the flow. That's how the mesh looks like, and you also put between your fabrics and your mesh. Usually you have a fall that you can peel it off later on and don't have the grid there. And for example, there you also have the slit walls, and they can have different hole size in there and different distribution of the holes. And depending on how thick your laminate is below, it can have an impact on the resin distribution, and if you get some porosity in the end there, if you get dry spots or not, and how everything is filling. And there, one of our PhD students, Lucy, she investigated also this topic a little bit more, and won last year award for a breakthrough in this characterization, where she came up with an analytical model to predict a selection criteria on the consumables to use. Yeah. Good. Then, of course, with all this input that we have on characterization, we do also simulations of the resin infusion on full scale. That's what we have recently done. That's on a 12.6 meter wind turbine blade, and I would say it's still work in progress. But I thought a nice colorful picture to bring here. But it's still not validated yet. But on a smaller scale, we have done a lot of characterizations and validated that. And also with inserts. So when you look into big wind turbine blades, usually they're not only made out of glass fibers any longer, but they have protruded, precasted carbon inserts that they put around. And of course, when you put this planks in there into the fabrics that should be impregnated, it's like a blockage effect, and you really would like to understand it, that you get a really good impregnation of the entire material. And this is what we tested on smaller scale, also where we built a kind of root section and or half part of it and model it, and then also compared to our experiments, and we feel very confident, so that we went to the next step and tried to do a full scale infusion. Then one more part that is also ongoing research in OptiCore. It's basically led by one of my colleagues, Rob, and all the work that I'm presenting here is far away from being my work. So it's also with a lot of my colleagues where I'm involved in it. But just to claim, so a lot of other people from my colleagues have here also authorship on their work. Is where they look in a little bit into the homogenization of the core flow for infusion simulations where they try to build up different models and then again come up with permeability equivalents for specific areas so that we can model it on big scale as well. Then work of one of my PhD students, Jesper Jørgensen. He looked into the exotherm and temperature development during the curing processes, where a lot of where the effect or the impact on different curing or cure kinetics, we call it, is studied. So how we ramp up the temperature after the infusion, and so which speed we ramp it up, how long we hold it, and then how we decrease it as well. What is the impact there on the residual stresses that occur? Then he built up a user subroutine coupled to the commercial tool Abacus, where we can then also can model it. And of course, for doing that, a lot of characteristics was needed in the laboratories as well to make the models reliable. But as what you can see here, the simulation match quite well the simulation. You have the temperature of the ocean, and then it's measured how it is predicted, and also then more or less the measure curve is following the simulations, or let's say the simulation more or less can predict what we have measured there. With that, we get a quite good idea on the impact of the cure kinetics on the residual stresses, and implement this then into a fine element software again. So meaning we do again a coupling of our simulated blade that we have, and couple then the residual stresses to the blade model, and then we can see, for example, that wrinkles can occur due to the residual stresses. And I think that is really a breakthrough. This work is quite amazing, I would say, because so far we could often see wrinkles, and I think all of the major players of the OEMs producing wind turbine blades have wrinkles, and so far it was always the goal to try to avoid or reduce those kind of wrinkles, and this really helps to understand the occurrence of the wrinkles. Before, there was always thought about, okay, what is the origin of the wrinkle? Is that due to the manufacturing that the labors, because it's quite a labor-intensive work, maybe had a small kink in there, and then it starts to origin. And here we could really show that the residual stresses have a big impact. And of course, now the only thing that we have to do is the difficult part here, and bring the university world together with industrial application, where they want to have industrial application a very short cycle time. And we show, on the other hand, that if you have a little bit longer cycle time, you reduce the residual stress, and that's beneficial. And now we have to find a compromise somewhere in between to make it really applicable. Good. Then when we have done all this characterization on small scale and done all the experiments, of course, we also want to manufacture our blade in big scale. And the purpose of our 12.6 meter blade, our DTU blade, we call it also our research and demonstration platform, is not just building a blade, because the blade is not impressive in size, it's not impressive in aerodynamics or anything there. It's just a representation of a blade, but it's cheap and it's easy to handle, easy to test. And we use it to build in defects and to study then the effects of the defects on the entire structure. And that's what we, for example, also do in here, where you can see there is the adhesive applied for the shear webs. So it's a butterfly approach where you have two shells that are joined, and in between you have shear webs. And here we implemented some slip foils with a specific pattern. So replicating that only 30 or 50% of the bonding is realized, like in real manufacturing, where not everything is always living up to reality, or to the wish as designed, let's say it like this. And then, of course, we incorporate this into our model and prediction, and later on we try to test it. Then, of course, maybe the following slide should have been before. First, of course, we manufacture one shell. Then we do this step. And then we get to the next step where we assemble the entire blade, doing the last parts together. And then, of course, demolding it. And when it's done with demolding, you get a blade out like this one, where you have the joints overlapping and you have to trim them off. So you have to manually work a little bit on it. And we are quite lucky. We have a very experienced technician with more than 20 years of work experience from Vestas that we could hire. And he's a great support for our team, I would say. Then after we have manufactured our blade, we run a test and scan the entire outer blade geometry. Because again, as we know, we had a CAD design that deviates a little bit due to the mold shape, but also then after we have manufactured it, it might also deviate a little bit. And then we run a scan of the blade and update our numerical model again so that we can incorporate it and those predict the stresses and so on a little bit better. Then running a lot of simulations, looking into model analysis and hope that our model predicts it in a good way, which is also giving us a little bit of, when the stiffness and the weight is more or less right, the models or the model analysis or response should be more or less correct on a global basis. And that's always the first step when we have a new prototype that we analyze. Then, of course, we also run testing. And usually for wind turbine blade, you can say around about 1/3 of the length of the blade. You can also deflect it because the newer blades are quite flexible. So we do static testing. And I think this is not so of interest any longer because there, of course, it's also important. But there we have showcased over the last decade, I would say, that our numerical prediction tools get very close also when we simulate ultimate strength or ultimate failure of a wind turbine blade. So we can basically model exactly where the fractures and how the fracture occurs. That was part of my PhD, I would say. There we are within a failure margin of 2 to 3%. So, and I think for such a big structure, it's very good. But of course, we also want to validate how everything works in dynamics under fatigue testing and how also new developed codes work. And one of the part is that, for example, we came up, and I will shortly go on to this one, we came up with a model. As I said before, we have our blade modeling tool that can discretize the blade structure with different element types. And then we also want to do the full experimental characterization or validation of our models. And for that, we came up with a novel idea. At least we extended a novel idea, I would say, by some point that we call now our blade property extraction method, where we try to, based on photogrammetry, digital image correlation, and so on, to calculate the bending stiffness of our wind turbine blade. And those can really relate it to our numerical model and validate our numerical model and how accurate and how good they are. And that's usually that we have different cross sections with markers, and then we have different load cases where we, for the static test, have usually 5 to 6 load cases where we load it in flatwise, edgewise, in combination and torsion and so on. And from the blade response, then we can extract basically the cross-sectional displacements and rotations, and we have the surface strength that we can measure. And then based on the mathematical approach behind it, we can derive the stiffnesses, the torsional stiffness, and so on, and that compared to our numerical models. And that will be published very soon. I just need a few more days to finish the article, I think, and then it will be out there. Good. I can see I have to hurry up a little bit. What I said before, our primary goal is that we want to validate with our experimental research that we do in the large scale lab our numerical activities, because we want to get more and more towards structural or virtual structural testing. And for that, of course, we need more confidence. What you can see here is the inner side of a wind turbine blade, where we have a LED light source that you could also say we illuminated for Christmas our wind turbine blade. And you can see a holder for a GoPro camera that we have installed there. And then we have some measurement tape and some markers for digital image correlation system. And with that, when we start loading our blade, then we can record the movement of the D-bond, for example. Now the goal is, of course, under a specific load condition that reflect reality of the blade, we want to load it. And then in static, it's quite easy. You put some forces there and load it. But of course, in fatigue, it's a little bit more difficult to predict, because on one hand, you need sometimes some dead mass to bring the blade exactly in the right frequency, because they are usually excited in resonance to save energy. But you also want to have a bending moment distribution that matches quite well that one exposed in reality. And for that one, we wrote our own test simulation tool, developed under a Blatik and Blatik 2 project. When we used all the stiffnesses and all that what we got from our numerical simulations, but also from our blade property extraction method into it as an input. And then we have a quite good input for our blade stiffness and response. And then we try to model it and also to know exactly in the virtual testing where we have later on to put our blade masses in the physical testing. And then we run a fatigue test, and there we have different methods. So we can just apply with hydraulics, and you can see there's a frame around the blade, which is our safe zone. So if it would exceed outside of the boundaries of some lasers specific area, then the test would automatically stop, so that we don't run any issues there. But we also have electric, see if it's working, electric exciter, where we have some push rods and some motors in the end, where we try to get to multi-axial loading. So where you can see we try to have these are two figures basically. Yeah, and here you can just see another one where it's more a single axis fatigue loading. Yeah, and then when we run these experiments, then we of course track our actual position of the blade tip, for example, and also know exactly the loading inside the blade. And then on the right hand side, you can see also the inside of the blade, where we again have our shear web and the movement. And then we can characterize or determine from our digital image correlation system how the D-bond looks and how fast the damage is growing inside the blade. And with all that, we get more reliability in our blade and also to predict damages. And by knowing, or when we have detected a damage, for example, in the blade, we are quite confident that we can predict and assist, for example, operators of wind turbine blades when they figure out with drone inspection or manual inspection that they have a damage somewhere in the blade, that we can say, okay, give us the properties of it, and we try to predict what we think will happen, and then they that helps them in the mentioning to either decide if the blade can still operate without a big risk for having severe problems, or if they should fix it, or if they have to replace the blade. And those that helps them to make more data-driven decisions and hopefully saving money. Yeah, and just for the last minute here, I just would like to show you one of our executable digital twins that we did in collaboration with Siemens Industrial Software 2-3 years ago. where we basically do augmented reality of a stress or of a strain field based on a blade where you can look through your tablet, film the blade moving live, and then the blade is equipped with some sensors. Here, because it's inside, it's still strain gauges, but we also have optical fibers. Then there's a B model inside that calculates it on real-time data. And now you can see the blade is excited. And you can see here on the tablet where it's augmented basically the strain field in the blade. Yeah. So that's, I would say, maybe so far doesn't have a real application, but it just showcases that you can do real-time prediction or data-driven or digitalization of it. And with that one, the project won an award last year for innovation in digitalization. Yeah, and with that, I'm coming to the end. Okay.
Okay, thank you very much.